In this online lecture, we're going to be talking about amines. These are the bases of organic chemistry. They are the compounds with nitrogen. Okay, so notice first of all that each of these nitrogens do not have a carbonyl on the carbons adjacent to the nitrogen. The nitrogens have carbons that only have other carbons or hydrogens attached. And that is the first thing to notice about amines. They have a nitrogen in them with no carbonyl attached to the carbon adjacent to the nitrogen. The nitrogen atom has a lone pair that loves to pick up protons. The nitrogen lone pair also acts as a nucleophile in SN2 reactions or even in SN1 reactions. So amines are weak bases and they are nucleophiles. To name alkenes, the simple alkenes, you name them as alkylamines or as, let's say, phenylamines. That's what the aryl stands for, is an aromatic substituent, like a benzene ring. So this is the way to name simple amines. There is a way to name them with the IUPAC method, where you name them as alkanamines. So a butane with an amino group in the number 1 position would be 1-butanamine. But for this course, this semester, all we're going to do is name the simple amines as alkylamines. We can classify them as primary, secondary, or tertiary, just like we did with alcohols. There is a difference in the way that you look at them, though. When we looked at an alcohol, we looked at the carbon that the alcohol was attached to. There's always just one carbon attached to the oxygen. So in classifying the alcohol, then what we do is we look at that carbon and see how many carbons are attached. And because there are 3 carbons attached to the carbon here, we call this a tertiary alcohol. And a secondary would have only 2 carbons attached, and primary only 1. But with amines, because they can have multiple substituents on the nitrogen themselves, we classify them according to how many carbons are on the nitrogen. A primary nitrogen has only 1 carbon attached. You see how there's only 1 carbon attached to the nitrogen. That's a tertiary alcohol. That's a primary amine. Here, a tertiary amine has 3 carbons attached to the nitrogen. And of course, if we have 2 carbons attached, then what we do is we call that a secondary. We also can name the amines as substituents when there is a higher priority functional group, such as a ketone or an alcohol. What do we do is we name the nitrogen part, the amine part, as amino. So what we do is we go to this molecule and we say, oh, the ketone has greater priority over the amine, so we're going to name this cyclopentanone and then put on the amine as a substituent. So what do we name this? We name this 3-amino cyclopentanone. There are also quaternary ammonium salts. Quaternary ammonium salts are amines that are a tertiary amine that has had the non-bonding pair covered up by another alkyl group. So there are 4 carbons attached. That nitrogen must have a positive charge. If you look at the formal charge, you would see there are 1, 2, 3, 4 electrons formally on the nitrogen. 5 is how much it would have in the Lewis dot structure when it's unbound to something. So it's deficient in 1 electron, so we put a formal charge of positive on it. And then there's the counter ion over here, for instance, a chloride or something. So these are really common because nitrogen is really nucleophilic and it will go and make this pretty easily. Okay, if we have more than one alkyl group on the nitrogen, we name each of them. If they are different, we would just name each substituent on there as an alkyl group. So we might have methyl ethyl propylamine, or we could have methyl ethyl phenylamine. When there are multiples of the same substituent, we use di and tri. So this is diphenylamine, and this is triethylamine. If we have different alkyl groups on there, then what we do is we name them as we pick the chain that is the longest one, and we name it as a propylamine, saying N-N-dimethyl. A lot of times we'll be sloppy and leave the N's off and say dimethylpropylamine, but that can be confusing because you might think that the methyl is on the propyl. So to be completely clear, what we do is we say N-N-dimethylpropylamine to show that those two methyl groups are on the nitrogen. So if I look at this, I find the longest chain, which is the cyclohexane. And then I say cyclohexylamine, and I add the ethyl and the methyl to it. So it's N-methyl cyclohexylamine. These are heterocyclic amines. You can have aromatic amines in which you have a benzene ring attached to a nitrogen, and that's considered an aromatic amine. Or we can have heterocyclic amines in where the amine is inside the ring, and that would be a heterocyclic amine. The only thing that I expect you to be able to do is to say this is a heterocyclic amine versus not a heterocyclic amine. Pretty easy to find the nitrogen in the ring and say it's heterocyclic. Or to be able to say it's an aromatic amine versus an aliphatic amine. And I have some problems to show that to you. Amines are bases because they have that non-bonding pair. That non-bonding pair is going to be held in an orbital, and you figure out what orbital it's held in by the hybridization of the nitrogen. This nitrogen here is an sp3 nitrogen, so the non-bonding pair is in an sp3 orbital. If it was an sp2 hybridized nitrogen, well, then the non-bonding pair would be in an sp2 orbital, etc. But what we're going to be looking at here primarily are sp3 hybridized nitrogens. How do you identify them? They're going to have three things bound to the nitrogen with a non-bonding pair on it. This gives approximately a 109-degree angle. If you have less than 5 carbons, the amine can hydrogen bond with water, and so it has water solubility. Primary and secondary amines can form hydrogen bonds with each other, as is shown here on the right. Tertiary amines do not have a hydrogen attached to the nitrogen. It is through that hydrogen on the nitrogen that they can hydrogen bond to each other. So a tertiary amine actually has a much lower boiling point than the primary and secondary amines with the same number of carbons because of hydrogen bonding between the amines in the primary and secondary amines. The amines have a lone pair that make them basic. They are able to pick up protons from acids in order to act as a base, which we're showing here in this reaction. Once they are protonated, they form a salt. The counter ion left by removing the proton, for instance here, the A-, is the other half of the salt. So when an amine reacts with an acid, it's protonated, and the positive ion with the counter ion make up a salt. Amines are stronger bases than alcohols, ethers, or even water. If you put amines in water, they react with water to make a small concentration of hydroxide. They are weak bases, but they are bases. You rate the basicity by protonating it and looking at the acidity. So if you ever can look up the pKa of the protonated amines, then you're able to figure out which is a stronger base. We're not really going to be rating the basicity of amines this semester by looking at which is more basic, which is less basic based on structure. We will do that next semester. But this semester, what I do expect you to know is if I give you a pKa of a protonated amine, that you would be able to figure out from the pKa which is the strongest base by finding the weakest acid. Amides are not amines. Amides have a carbonyl attached adjacent to the nitrogen. So here is an amine. There is no carbonyl attached adjacent to it. But here is an amide because the carbonyl is attached to the nitrogen. That makes it an amide. These are non-basic because the non-bonding pair here gets tied up in the pi system of the carbonyl. So we consider amides to be non-basic. Amines are basic. The carbonyl has a tremendous effect on that non-bonding pair and makes it non-basic. If you take an amide and you put it in strong acid, you can protonate the amide, but it does not protonate on the nitrogen, it protonates on the oxygen instead. And that actually makes sense. By looking at this resonance structure, you see where there is negative charge primarily residing in this. There's positive charge put on the nitrogen by the resonance structure, negative charge put on the oxygen. So when you put an amide in strong acid, the proton actually protonates the oxygen and not the nitrogen. They are non-basic nitrogens. Here are some heterocyclic amines. These are common in biochemistry, and when you take biochemistry, you'll see them various places. Amines, you have already seen that nitrogens will act as a nucleophile and that they can do SN2 reactions. So if you have a primary or even a secondary alkyl halide, and you mix it with a compound that is either ammonia or amines, you get SN2 reactions. And so if it adds once, you get a primary amine. If ammonia adds once, you get a primary amine. If a primary amine reacts with an alkyl halide, it'll give you a secondary amine. If a secondary amine reacts with a halide, it'll give you a tertiary amine. And a tertiary amine will actually react with an alkyl halide again to give you a quaternary ammonium salt. And this looks like it's all the same reaction, and it is. The SN2 reaction is hard to stop. So when you mix ammonia with an alkyl halide, even if you just mix 1-to-1 stoichiometry, you're going to get a mix of products. You're going to get not only the primary, but the secondary, tertiary, and quaternary ammonium salt present in there. Now, you might have mostly primary amines, especially if you use a huge quantity of ammonia. You can shift the reaction to doing just the first reaction so that the number of ammonia far outnumbers the number of primary amines made, so it's unlikely for the primary amine to undergo the SN2 reaction. But other than that, it's really hard to control this SN2 reaction. So next semester, we're going to see there are ways of making amines the way you want to make them when an SN2 reaction is kind of hard to use. So now we're going to try some problems, and what I want you to do is select the best classification for this amine. Is it primary, secondary, tertiary? Is it an aromatic amine, or is it an heterocyclic amine? Well, if you look at it, you can see the nitrogen is not inside the ring, so it's not a heterocyclic amine. It's not an aromatic ring because this is not an aromatic. You don't have the double bonds in there, so it's not aromatic. And so we know it's aliphatic. How many carbons are attached? 2. So this is a secondary aliphatic amine. Which of the following is not would not be able to be used to classify this amine? Well, if I look at this, I will see that, first of all, it is a secondary amine because there's 2 carbons attached, so that works. If you look back at the heterocycles, you will find that pyridine has this structure, so it is a pyridine ring in there. And it is a heterocyclic amine because the nitrogen is in that ring. The only thing that you don't see there is a saturated carbon chain, something like an ethyl or a methyl or a propyl or a butyl. That's not on here, so this is the classification that does not fit. Name this compound. Well, you can see that there is an ethyl, there is a propyl, and there is a phenyl. The phenyl has more carbons, so we're going to name this as a phenylamine. So it's N-ethyl, N-propyl, phenylamine. What is the product of protonation of pyridine? This is pyridine. Well, if I protonate it, where is the proton going to add to? The non-bonding pair on the nitrogen. So if I protonate it, you get the hydrogen on the nitrogen and it has a positive charge. Notice there are 4 bonds on that nitrogen now.